Hey guys, welcome back to part 8 of coding asteroids in TypeScript. Today we're going to take a look at collision detection, specifically the point or a bullet to a polygon collision. So a bullet versus either an asteroid or bullet versus either a player ship, for example. Okay, so let's go back to our code editor. And before I actually start working on the collision detection, I want to address one issue we had last time with the shooting. That was that if you hold your space key down, it keeps shooting, and in the original game you have to lift the key up. So let's fix that first. So I'm gonna go back to my game, actually the player ship, and where did we do the shooting? Here, we did that here, right? So let's get rid of that. Actually no, let's keep it here for now. I'm gonna go back to our keyboard and I'm gonna define a new field called down key once listeners. So the idea is that each time you hit the key down, you invoke some listener, but every time you repeat the same key, like if you're holding it down and you get multiple events while you're holding the key down, those are not gonna trigger this listener. It will only trigger it once. I mean, you could have done it on key up as well, but there's a latency with that. So every time you lift the key, only then the bullet shoots. The cannon shoots. But we want to have it on as soon as you press the button, it shoots. But then to shoot again, you have to press it again. So let's define our key listeners as a map of key to some listener, and I'll define it as a set because you can have multiple listeners for one key. And actually we don't need multiple listeners right now. Each key does just one thing, right? So first let me define a new type here. Type listener is just gonna be a void callback. I don't even know if you need a key here though. I don't think we need it for now. So let's just specify an empty function and initialize it here. Down key once listeners, new map, and then in our handle key press we will check if e dot repeat. So repeat we can use, it's a boolean field that every time it just marks the event if it's a repeated event or if it's like the first time you're pressing the key. So we want to check if it's a repeat event, or you want to check if it's not a repeat event. So if it's a first time event, you want to invoke the listener, right? So you want to say this dot down key once listeners get key, and if you have that, then you just invoke it, right? Okay, and you also want to do it on key down, so you probably want to do that here. And let's define a new registration function. So we will say on key down once. Yeah, so we will say key is a key, and we'll take a listener here. So listener, and then we will say this dot down key once dot get, I will just set directly key listener. Okay, So now if I go back to our player ship and I go back to where we have the input, I mean the canon definition. So in here now we can say this dot on input dot on key down once. Then you wanna pass in key dot space, and we can say this dot canon dot base. My bad. You basically want to have whatever we had here, this part. So I'm gonna take that. Okay. Yeah, and if I go back here, we can delete this. Now let's try that. Okay, I'm holding down the key, but it only shot one bullet. I let the key go, nothing happens. That's good. Press again, it shoots. Okay, perfect. All right, now back to collisions. So let me first define a new type called collider. Right, so I'm just defining it as a type that will, because in this game we have a few different type of collisions, right? So we have point to polygon, and we have polygon to polygon. So point to polygon example is like bullet hits asteroid. Polygon to polygon is ship hits asteroid, right? Or saucer hits asteroid, right? Just some examples. And today we're going to focus on just the point polygon collisions. So yeah, let's get that going. I'm going to define a new collider type first. So let's say collider. So what is a collider? So a collider is going to be it could be multiple things, right? So it could be either a point collider, or it could be a polygon collider, right? So now we are defining two different collider types, and for each of these I'm going to define new types. Point collider is something that just has a position, right? Because our point is just a point, right? There's no size to it. Or we can just assume some fixed size for the entirety of the game. That doesn't matter. Yeah, after that, let me import this. So we can also define our polygon collider. So it will be similar, it just have a position, and it needs to have the geometry, right? It needs to store each of the vertex. So all the vertices need to store for a polygon. So I'm gonna wrap all of that into a new class called polygon that we need to create, and then this type is good here. We just need to create the polygon class. So we can just create it here. We can say export class polygon, and what is going to have it's going to have we can have them public position, and it's going to have geometry. Geometry will be all the vertices, so array of vectors. Okay, and what we also want is in here It's fine. Let's just define polygon for now, and then we will also export each of these. Okay, now we will set up some boilerplate for the collision detection. Actually, what we're gonna do first is we're gonna add a new method on our entity interface called collider, and it's gonna give us back a collider. Import the collider. So what we're gonna say is that all the entities in our game, they should have some collider, right? I mean, we are not using any sort of component system here because it's a simple game, so it's fine to have some of this behavior on the entity itself. Usually what we would do in a big game is you have some sort of entity component system or decoupled components from the entity, but we're not gonna do that for this game. So now I'm gonna go back to each of our entities. For bullet, for example, now we will implement collider, and it's going to give us return new. I mean, it's just a point collider, right? So we can, how will it know it's a point collider? We can go to collider and do something like this. We can say type, and we can create a new enum here. Export collider type is equal to enum. It will be point and polygon, and then we can say we can say here type is collider type dot point. We'll do here polygon. So we mark this type as a polygon type, and we mark this type as a point collider type, right? That way it's going to be easier for us to deal with the actual values of these colliders rather than just this interface. You will see when we start the implementation. So now if I go back to here, now if I say type collider type dot no polygon point, TypeScript will know by itself that this is just a point collider. You see, so it's not gonna give me polygon here, it's only gonna give me position. That's the benefit of this approach. Now, so we will return this dot pause dot copy. We don't actually need the copy here because you're just going to read this position. You don't need to mutate it, but it's fine. It doesn't hurt to have its own object. Okay, so we do the same on asteroid. Collider, but this time is going to be polygon, and we will say polygon is new polygon. Position will be this position dot copy, and the vertices will be this dot vertices. It's fine. We don't actually need the copy because I don't want to copy the vertices as well. We're just gonna have it read only, so it should be fine. And we need, what do we need? Position. Oh, we don't you actually need position in on the glider itself because we already put it in the polygon. So now if I go back to asteroid, it should only have this, and I'm gonna go to the player ship now. Yeah, we can do it here. So same thing here. Do we know how vertices? Oh, we have that in the draw. Yeah, I think in the first episode of this series we had them here, and we said we'll move them out later on. So let's do that now. I'm gonna define them as a constant here, and I'm gonna rename these to ship geometry, and we will take this off, and I will say first I gotta go back to the draw, and I will say cost vertices is equal to ship geometry dot whatever was there before, and so this, it will be ship geometry. Yeah, this looks okay. Yeah, this needs to be vertices because they need to handle rotation. All right, now okay, bullet already has it, right? Yeah, let's go to our game, and first thing I'm gonna do is I want to actually look at the point in polygon collision algorithm. So in order to do that, right, so first I want to visualize that, and we can work on the algorithm on like iteratively. So what I want to do here now is that so I'm thinking that we will draw some polygon on the screen somewhere. We'll fix it there, and we'll draw a grid of points around it, right? And then for each point we will test if it's inside the polygon or not, and based on that we'll switch the color of that point, right? So that way we will be able to easily debug what's happening with our algorithm, right? So let's do that first. So first okay, I think I'm gonna go to draw, and I'm gonna do some yeah, so I'm gonna say export function raw debug grid, and then this will take a position, right, and a size, and some check function, right? It will say like some predicate will take point vec2 and return a boolean, right? So we want to make it generic to some any predicate. If that predicate responds with true, we use a different color on that point. So I'm gonna say for at I equals 0 and I less than size I plus plus. Actually, let's rename that to x, and then I'm going to copy the same for Y. And I'm going to say I'm going to say draw x, well, no, px is equal to position, wait, I want to say like the offset equals position dot add new vec to xy. Actually you want to start from the negative, right? So you want to start from minus size, because I want the grid to be centered around some point, then this position. So I will say const offset position dot add this offset, and well, actually this is the offset, right? So I will say point position is equal to position dot add offset, and then I will say if I will say I actually need the context as well here to draw this grid, and then we will say if predicate point then context dot fill style equals green, something that we can see, else is red, some obvious colors, and then we will do a fill rect or a fill circle. We already have fill rect, so let's reuse that. So I'll do a fill rect on point pass dot x, point pass dot y. Now I'll do 1 maybe, and I'll do another 1 here. Okay, now actually I want to move not just by 1 pixel, I want to be able to move by a few pixels, otherwise we're just gonna see a huge blob, continuous blob, and I don't want that. I want the each point to be visible. So I'll say 5 here. Okay, now let's use this debug grid in our game, and the first thing I want to do is I want to reuse this asteroids geometry to draw a polygon. So what we can do is we can say polygon collider is polygon collider, and then I'm gonna take out this asteroid. I'm gonna say const asteroid equals new asteroid, and then I'll push the asteroid here as well, and then I will say this dot polygon collider is equal to asteroid dot collider, and I'm gonna force it to be polygon collider because we are just testing collisions right now. Later on we won't need to do any of these casting. Okay, so let's go to our draw, and we will do some debug drawing here. So we will say draw debug grid, and then it will be at this dot polygon collider dot polygon dot position, and then wait, actually the first parameter is the context. After position is the size, so let's say 50, and then we have our predicate, so that will be point. We can just do that, point, and I will say return check, or not check collision. I will just say point inside polygon, and I will pass our point, and now I will pass the polygon. So we will create this function in a new file. So let's create this function. I'm gonna go back to our folder and create a new file called collision.ts, and I'm gonna say export function point inside polygon. I'm gonna pass in the point, and I'm gonna pass the polygon. So we will return a boolean, so I'm just gonna start with return false. We will do our implementation here. Get the imports. Okay, now go back to the game, import this function, and let's see if we get anything on the screen. Okay, we do see our debug grid. That looks pretty good actually, and I want to stop this asteroid, so let's stop it in the let's give it 0 velocity, and I'm gonna force it to be in the middle, so I'm gonna say center, and I'm gonna move our player to the top left corner so it's out of the way. Okay, let's just make our asteroid bigger. So I'm gonna go actually here. I'm gonna comment this for now. I'm gonna say maybe 20, or even bigger. We can do 25. Okay, that looks okay. Now we go back to the game, and let's increase the size of the debug grid to 100 maybe, or even more, 150. Okay, perfect. Now actually let me give it some width, each point in here. So I'm gonna say 2, yeah, much better. Okay, now let's go back to our collision. Let's try return true. Okay, yeah, looks good. Now based on if the point is inside the polygon or not, we will return that appropriate boolean. Now let's see, how do we calculate if a point is inside a polygon or not, right? So what we are going to use is we're going to use an algorithm called raycasting algorithm. So if you search for point in polygon on Wikipedia, you get this. It's a very common algorithm. It's called the raycasting algorithm. What happens is that you take any polygon, it could be either a concave or complex polygon, doesn't matter, and you take some point and you measure the intersections for that point in one direction through that polygon, right? So for example, if I take a look at this picture, right, we have one collision, one entry here, exit here, so that's 2. We got 3, 4, 5. Then we probably got 6 here as well, right, at the end here. So what the algorithm says that if you count these intersections and if the value of these intersections is an odd number, then the point is inside the polygon. And if it's an even number, it's not inside the polygon, it's outside. And why does it matter if it's odd or even? I can't explain that. It's something to do with this Jordan curve theorem, which goes into how it divides the space into an inner region and an outer region, and it gives this property that if anything enters it and then exits it, you basically get even number of intersections in one direction. We don't need to go into that too much. For our use case, is we should just know that if you pass in one ray in one direction to a polygon, to count the intersections, if it's odd, then the point is inside the polygon. If it's even, then it's outside. So now how do we actually compute this, right? Yeah, well, this is the same thing I just mentioned. If you have the point outside, you count the number of intersections, and you see this is even, and for anything that's inside, you will see always it's going to be an odd number of intersections, right? Same thing here, 1. For anything outside, you get even, and this is already outside, right? So what we want to do in our case, right? So how do we represent this programmatically, right? What we are going to do is we're going to take our point and then iterate over all our edges, and then verify that the point is left of that edge, right? And then count if it actually intersects or not, right? So for example, we will go like, take this edge and then count this, check if this point is on the left or the right. If it's on the left, we count this as an intersection. Go to the next edge, do the same thing, and then go to the next one, and then go to the next one, and then we count all those intersections, and then if it's an odd number, the point is inside the polygon. Okay, so now how do we actually calculate this intersection, right? So I'm gonna zoom in to this part a little bit, right? So I'm gonna define a point and one single edge of the polygon. Okay, we have that here. So if you look here, this is our point that we want to test, and this is that one edge of the polygon, right? And we want to find the x-intersect, right? This intersection point. We have the vertex 1, which is x1, y1. We have vertex 2, x2, y2. And based on these three values, we want to compute the x-intersect, right? I mean, we also want to determine if the point actually lies within this region, because it could be that the point is just like here. Like if the point is anywhere in here, it doesn't matter. Point anywhere in here, there's no collision, right? Same thing. Point is here as well, it doesn't matter. We want to make sure the point is on the left side. So any ray that goes from left to right, it does intersect with this edge. Okay, so how do we compute this, right? So we are going to use slope, and we're going to do some linear interpolation to get that done, right? So if you look at this value here, that's y2 minus y1, and if you look at this value here, that's x2 minus x1, right? So we can compute the slope with this, and I have that math right here. So I'm gonna pull that first to the left side, just so we can see it all at the same time. Okay, here we go. So wait, I'm gonna move it here so we can see it on the screen. All right, so if you look at this, right, so we have the slope definition, and we can define the slope in two different ways. One is actually, let's first look at the number 2. The one I just talked about is y2 minus y1, this value over this value. So it's rise over run, right? So that's this slope. Now we can also define the slope as this rise over this run, right? Because it's the same thing, right? So we had this before, and now we can use just the x-intersect point and the difference from that to the original point, right? So we can say this value yp minus y1, so yp is the y of the point, and then divided by the x-intersect minus x1, right? This one. So x-intersect is here, x1 is here. So we have basically this value. Now we get two different definitions for the slope, and we can equate these to each other, and we are basically gonna get this equals this, right? I mean, first we're gonna expand this a little bit so we can move the denominator to the other side. We get this, and then we move slope to the other side because we just want the x-intersect. We're gonna move all other terms to the other side. We get yp minus y1 over slope, and we just have the x1 on this side. We push it to the other side, and we get x1 plus yp minus y1 divided by slope. And now based on our other slope value, which is based on our known vertices, we can plug that right here, right? So this is the same value here, and the slope is, since it's in the denominator, when you multiply it, it will become inverted, right? So this is the same thing as, this is just 1 over slope, right? So you can think of this as yp minus y1 multiplied by 1 over slope. Yeah, so now we get the x-intersect, right? So we get this point. Now if the actual point position lies on the left of this x-intersect, we have an intersection, right? So that's what we want to check. Now we do this for each edge of the polygon, right? And then count how many intersections we have in total. Okay, so let's start doing the implementation. So maybe it will be useful to have this on the left side. Okay, we'll keep referring it here. So first thing we need is we want to be able to loop over all the edges. And since we store like just like we store like for each polygon, right? We, let's say I have some polygon, right? We only store like each point, not including the first point, right? So we don't have this edge here, so we need to wrap to the first point again when we do our iteration. So let's go back. I'm gonna leave it here now. So one thing we can do is we can go to our polygon class and define some sort of iterator over wrapped vertices, right? So we can define a generator again, similar to how we did it for entity collection class. And I will say vertices closed, right? So we will loop over our geometry, right? And we will get the vertex. I mean, we want the edges, we don't want the vertices, right? Let's do edges, and then we can do, we need the current one and another one, right? So we will do, actually we can just do this, it's fine. So VA equals this dot geometry I, and then I'll say VB this dot geometry I plus 1, and I will do a modulo on it so it wraps around to the first element. This dot geometry dot length, and we want to be able to, we want to add our position to these geometry as well, right? Because we want not the local, because the geometry is just relative to some origin which is 0 0, right? We want to offset it by the actual polygon position to get the absolute position of that vertex. So we will say this dot position, and then we will do the same thing here, this dot position. Now we can do yield VA VB, right? Let me take a look at the return value for this. Yeah, I'm going to specify it here to be a generator of two vectors, right? So it's just an edge from one vertex to the another, one vertex to another, and I think we just need the edges, right? Okay, go back here. Now we will loop over these edges. So we will say const VA VB of polygon dot edges. We get rid of our return, and I will say here we want to count the intersections, right? So I'll define that as 0, and then we want to return a collision only if the number of intersections is odd, right? So we can do that here right now. Now the first thing we want to check is, like, if our point lies in here or in here, so we have no collision then with this, no intersection with this edge. So we can check that case first. So we can say within Y, let's first expand our point. I want to say X as PX or XP, Y as YP equals point, and then I want to expand the vertices as well. So I will say X1, Y is Y1 equals VA, and I'll do X2, Y2, VB. Okay. Now we are within Y. If you check that the point YP is greater than Y2, which is not equal to YP greater than Y1, right? This is a handy condition to not do the min and max. For example, if you had an edge that goes, instead of like this, it is like this, right? Then your Y1 is at the top and Y2 is at the bottom. Then you need to take consider the order, right? So what we can do instead is we can either do like a min Y is equal to math dot min y1, y2, and then a max, and then do two conditions, that whether the yp is greater than min y and less than max y, or you could just do this, right? This is a shorter way to say the same thing. Now if we say if within y intersections plus plus, let's see what happens. Okay, nothing happens. It's just because we are doing this right now. So if you say, for example, intersection greater than 0, if you get any intersection, that's actually not the x intersection, it's just the testing if you're in the y range, then only the y range, the points that are in the range of the y value of the polygon, it should match. Yeah, so whatever is in our y range, we can validate the, now they are marked as colliding, right? So that's the first step. This is actually not the condition. We'll get this back, and then what we want to do is get rid of this, and we want to compute if it's within x, right? And we will say something here. Let's say we just say false for now. This is to do, right? And then we want to say if within x, then you want to do intersections plus plus. Yeah, so how do we compute within x? So we need to compute our x intersect. So if you look at the formula here, we need to compute our x intersect, and we need to check if our point lies to the left of the x intersect, right? Or if it's less than the x intersect. So let's take these values. We can actually use this formula, because then we can compute the slope easily. So first let's compute the slope. I'll leave the x intersect there. I'll just say slope is equal to y2 minus y1 divided by x2 minus x1. I'm gonna wrap these. Okay, we got the slope. Now we gotta do this, and we will say, yeah, we can just do it here. X intersect is equal to x1 plus yp minus y1 divided by slope. Okay, and then we can say within x if xp is less than x intersect. Okay, and then get rid of this. Let's try that. Perfect, look at that. That looks nice. Okay, one thing we can do is instead of adding and then checking if it's odd, we can just flip it left and right. Like a flip a value, we can just say let inside equals false, and then in here you can just say inside is equal to not inside, right? And then return inside. So you just flip it back and forth. How many times you flip it, it's basically the number of intersections, right? So if it's odd, you flip it to true. If it's even numbers, it goes back to false. There you go, same thing. What else? Yeah, one thing we can do is we can, like, for example, like these edges, right? So if I zoom in, like if a point is right on the edge, there might be some floating point precision issues that we might want to deal with. Like you can just force, like if the point exactly matches the vertex, you can just double check that in here. We also got to make sure that the slope is not 0, because you're dividing it by 0 here, and that means x2 minus x1 needs to be 0, right? So we want to say if slope is 0, you want to just continue. You just want to skip that edge from counting the intersections. It would be as if the ray just glanced by. Okay, now let's take a look if this works. Such a nice little visualization. Yeah, so everything that's green is just, I mean, some edges could be better, like these ones, they're a little bit touching, but I think it's good enough for this game. Yeah, I think we'll do the integration with the like for example, when the bullet hits and what happens and things like that. We'll do that in a later episode, but this is already looks pretty good to me. So I'm gonna call it for today here. The video has been already pretty long. Yeah, we'll do, I mean, the one benefit of having this grid here is that we can just replace these points with some polygons, and then next time we can just test polygon with the polygon collisions. Looks pretty good. Yeah, we'll do some more integration work next time. Thanks for watching.